Hey, my name is Rishi Patel, and this is my Physics 2212 Lab 3 video report. The purpose of this lab is to obtain a better understanding of magnetic fields for a dipole. To understand this concept, we can use the distance dependence of magnetic fields and compare these values to predictions made by equations from the PHYS law. I found that from calculations, n is equal to -2.8955, k is equal to 6.911 times 10 to the negative 7th, and mu is 3.456. From the computational results, I found that I got 3.586 times 10 to the negative 5th Tesla. The fundamental concepts and principles for this lab is modeling a bar magnet as a dipole and visualizing the magnetic field, the distance dependence of the magnetic field, which is found by this formula, Kr to the nth power, linearization for modeling, which is very important for graphing our data, and also the Beat-Savart laws. The initial conditions for this lab involve the phone with the magnetometer app placed on the ruler based on the setup to the left, and also the system, which is the bar magnet. Before beginning the first part of the experiment, I calibrated the setup to account for the Earth's magnetic field. Then, after identifying the location of my smartphone's magnetometer sensor, which is seen by the visual on the slide, I was able to make measurements based on the location of the bar magnet. I did this 3 times for 5 different locations. As seen from my data, I chose 5 different distances and they correspond to different x component values for the magnetic field. After linearizing the data and plotting it, I found that my n value is negative 2.8955, which is the slope of the line, and my ln of k value is negative 14.185. The next part of the experiment involves measuring the off-axis magnetic field. To do this, I changed my setup so I could use distances off the axis. After finding the x, y, and z components of the net magnetic field, I corrected the y component and computed the magnitude of the net magnetic field. The observations that I made is that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. Also, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here are some important calculations. From the line equation, I found that n is equal to the slope of the line, which is negative 2.8959. The natural log of k is equal to negative 14.185. To find the value of k, I isolated it and raised each side to e, which resulted in 6.911 times 10 to the negative 7th. Also, I assumed that r is equal to 1 when doing the further calculations. Next, I found an expression for mu. To do this, I used both Beat-Savart laws and simply set them equal to each other. In doing so, I found that mu is simply equal to 10 to the 7th power times k times r to the nth power times r cubed divided by 2. After plugging in my known values, the answer that I got is 3.456 area times a meter squared. Next, I have the code that was done on GlowScript. I created a function that calculated the magnetic field based on various locations on the axis and also perpendicular to the axis. I also have the 45 degrees off axis, which is based on the perpendicular distance, which was measured in the second part of the experiment. Here's a visualization of my code. The blue and orange arrows represent the on-axis perpendicular and parallel magnetic field. The purple arrow represents the 45 degrees off-axis magnetic field. Next, I will compare the results from the experimental calculations and also from the computational model. From the experimental calculations, I calculated that the magnitude of the net magnetic field was roughly, on average, 5.145 times 10 to the negative 5th power Teslas. From the computational model, however, I got a very different answer, which is 3.586 times 10 to the negative 5th Teslas. Errors for the final result may have derived from systematic and random errors throughout the experiment. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? Well, my results would have been off because of interference from the Earth's magnetic field. This would have led to inaccurate results for both parts of the experiment. What if you were to stick 2 identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? Well, the measurements in the experiment would have increased and potentially doubled because the magnetic field would have combined and increased accordingly.